Question 3 says to use the cofunction identities to write an expression that is equivalent to each of the following expressions. So A, I have sine of pi over 6. And it's telling me that I need to apply the cofunction identities. So the cofunction identities were a few of the formulas that we developed in our various classes so far. So let me scroll out here. So here's our formula sheet, our handy dandy formula sheet. And here's what our cofunction identities state. Okay, so here it's saying that if we have sine of theta, we can write that instead using cosine by having some sort of like translation left or right. We saw that with the graphs that kind of clicked in. Same with tan to cotan or cosine to sine, okay? So in this case, we're given sine of an angle. So we know that we have sine of pi over 6, and we want to find an expression that's equivalent to sine of pi over 6, okay? So in that case, I know what sine of theta is. Therefore, I can convert that to cosine of some angle using that formula. So the formula that I'm applying here, sine of pi over 6, or sine of theta, rather, sine of theta, equals sine, or equals cosine of pi over 2 minus theta. Okay? And in this case, our theta value is equal to pi over 6. So let's apply that formula now. So sine of pi over 6 equals cosine of pi over 2 minus pi over 6. And then we just need to simplify the bit inside the brackets here, right? We're subtracting two fractions, so we need a common denominator. And then we can go forward and subtract. So this will be equal to cosine pi over 2, you can write that as 3 pi over 6 minus pi over 6. And then 3 pi over 6 minus pi over 6, that is cosine of 2 pi over 6. And then we can reduce that fraction. We can simplify that a little bit. So cosine of pi over 3. Okay. And so now that expression that we found, cosine of pi over 3, should be the exact same as sine of pi over 6, right? So let's grab Wolfram alpha here. Oops. So if I type sine pi over 6, it should give me an exact value. Yeah, so sine pi over 6 is 1/2. So 1 over 2. And let's check cosine of pi over 3. Also 1/2, right? Also equal to 1/2. So we have two different trig expressions, sine of pi over 6 and cosine pi over 3, but those are exactly the same thing, right? They mean the exact same, they give us the exact same value. Okay.
How does it give you like 1 over 2 though?
Well, this is one of our special triangles, right? Pi over 6, pi over 3, those are.
Right, yeah.
So I didn't have to use Wolfram alpha here. I was just being really lazy. So I could have instead recognized, oh, well, I have pi over 6, pi over 3, and then I have 1, root 3, and 2. So if I'm looking at pi over 6, sine of pi over 6 is the opposite over the hypotenuse, so 1 over 2. And if I look at cosine of pi over 3, again, I have 1, which is my adjacent side now, over 2. So essentially, they both equal the same thing. They're both part of a special triangle. Any questions about that type of question? Turning one trig expression into another one using cofunction identities? Okay, let's try one more here, and then I'm going to go grab a cup of coffee, and maybe you can try a couple yourselves. So let's try cosine of 5 pi over 12. So let's try b. So 3b, we have cosine of 5 pi over 12. So again, for this, I go to my formula sheet, which you can find at the very end of your assignment that I posted for this unit. And I recognize that I have something that looks like cosine of an angle. So I come to my cofunction identities, and I'm told that for my cofunction identities, cosine of an angle is equal to sine of pi over 2 minus whatever that angle is. And in this example, the angle that's given to us is 5 pi over 12. Okay. So now we can use this formula to rewrite this trig expression. Okay, so cosine of 5 pi over 12, so that'll be equal to sine of pi over 2 minus 5 pi over 12. Now I have to simplify the brackets, and in order to do that, what I have to do is find a common denominator again, right? So we have sine of pi over 2, that's 6 pi over 12, minus 5 pi over 12. So I found a common denominator, and now I combine the two terms, right? So 6 pi over 12 minus 5 pi over 12, that is sine of pi over 12. And so I have found this value. Now, sine of pi over 12, pi over 12 is not a special triangle. So in this case, to actually evaluate what this thing is equal to, I would have to actually pull out my calculator or go to Wolfram Alpha to actually plug this in, right? Now this step is kind of optional, right? Like once I've found this, once I've found sine pi over 12, I'm done. This problem is finished. But I like to make sure, right? I like to verify my answers. So let's just make sure. Cosine of 5 pi over 12, when I plug that in, this is equal to, well, the exact result is kind of messy, but the decimal approximation isn't so bad. So 0.2588. And let's just check sine pi over 12 to see if that changes at all. Sine pi over 12 also equals the exact same decimal approximation, right? Also approximately equal to 0.2588. Okay. So how do we feel about cofunction identities?
Good.
Good?
A little better, yeah.
A little better? Nice, nice. Okay, how about if you guys want, give, on the same page, give C or D a try, okay? See if you can get those right. I'm just gonna go refill my coffee and then I'll be back in 2 seconds, all right?
Okay.
All right, coffee is acquired. Did someone try 3C?
Yeah, I got cotangent, right? Pi over 8.
3 pi over 8. So you found cotan of pi over 8. Okay, cool. I think that checks out, right? Because 3 pi over 8, so pi over 2 minus 3 pi over 8, I think that is equal to pi over 8. And again, we can actually check. If we just do tan of 3 pi over 8, and we can just do an equal sign and then cotan of pi over 8. The way that Wolfram Alpha interprets something like this is it says, okay, I have the left-hand side of an equation and I have the right-hand side of the equation. Are those two equal? And then here we can see that the result is true. And the result being true tells us that those two sides are equal, right? So nice, easy way of checking stuff like that, right? Aiden and Ava, did you give this one a try?
Yeah, I was working on it.
Working on it? Okay, cool. But how are you guys finding this? Pretty
It's decent, I guess.
decent? Nice. Okay. Ava, how about you? Is this seeming pretty okay so far?
It's
Okay, okay. I'll take that. Let me just fill in the details for this one, just to give you guys one more example to work with here. So again, let's go back to our formula sheet here. So we know that the cofunction identities, we know that we have tan theta equals cotan of pi over 2 minus theta. And in this case, our theta is equal to 3 pi over 8. And so we have tan of 3 pi over 8 equals cotan of pi over 2 minus 3 pi over 8. We find a common denominator for the term inside the brackets. So cotan of 4 pi over 8, that's pi over 2, minus 3 pi over 8. And we get cotan of 4 pi minus 3 pi, that's just pi over 8, which sounds good. Natalie, that's what you got. Checks out. Everything looks good. Okay, let's move on to a different type of example now. Okay, so that was number 3 on the homework there. So 3 gone. Let's try 5. 5. Okay, so 5, we have to write an expression that is equivalent to each of the following expressions by using the related acute angle, okay? Now, this one's a little bit more involved, slightly more involved, but yeah, let's try it. So 5a. So here we have sine of 7 pi over 8, okay? So in order to do these types of problems, the key to this question is all to do with the related acute angle, right? That's kind of why the question mentions that in the phrasing of it. So in order to do these problems, what we have to do is we first have to figure out what quadrant this angle falls in. So yeah, let's write that in red. Which quadrant is theta equals 7 pi over 8? Any ideas? Anyone want to hypothesize which quadrant that's in? 7 pi over 8?
How would we?
Would it be in 2 or 1 or 2? I'd say.
Okay, Aiden, what were you going to say?
I was asking, like, how would we know just from looking at it?
So the way that we know this, now Natalie, you said 1 or 2. I'll get to that in a second. So it turns out that this angle is in quadrant 2. So let me show you how I know that. So 7 pi over 8. This is kind of where radian measure comes in really handy. When you think about this as a fraction, it kind of makes everything a lot easier. So imagine we know that this is 0, this is pi over 2, and this is pi, right? 0 meaning 0 degrees, pi over 2 is 90 degrees, so 90 degrees, and pi is 180 degrees, right? Now, I mean, in order to solve this, what you could do is like convert it to degrees and then figure it out that way. But it's almost easier than that. The way that you want to think about this is not pi over 2 and pi. What you can do is you could recognize the fact that this expression is over 8, right? The fraction that our angle is found in is something divided by 8. And so what we can do is we can convert these to have a denominator of 8 as well. So pi over 2, we can think of this as 4 pi over 8, right? I haven't changed anything. Pi over 2 and 4 pi over 8, that means the same thing.
Yeah.
And similarly with pi, Aiden, how could I write pi as a fraction over 8?
You'd have to could you just put it over 8?
Yeah, well, over 8, but yeah, I agree with that. So like pi over 8, but you have to make sure that this will equal 1 afterwards. So this will be 8 pi over 8, right?
Oh.
But see how I've not changed anything? 8 pi
Yeah.
over 8 is the same as pi. It's just a weird way of writing. You know
Yeah,
what I'm saying?
that makes sense.
Cool. So now in this case, I look at the numerator of my fraction, right? I notice that my numerator is 7. And so looking at that, it should be kind of clear that, oh, well, 7 is between 4 and 8.
Yeah.
Therefore, we're in quadrant 2.
Yeah. Okay.
Does that make things a little bit more clear?
Yeah, that makes a lot of sense.
Nice. Okay. And that's, honestly, that's the reason why radians are so nice, is because everything kind of breaks down into a nice fraction. That's the reason why we use that in the first place. I kind of keep saying that, like radians are actually kind of nice to work with.
Yeah.
This is the main reason why they're nice to work with.
Okay. Yeah, that makes sense. That makes sense.
Nice. So our angle here is 7 pi over 8. So this isn't to scale. It doesn't need to be to scale or anything like that. Now our related acute angle is tucked away in here, right? Here's our related acute angle. Okay. So in this case, what does anyone have an idea of what the related acute angle is equal to?
Should you just do like wouldn't it be pi over 8?
It would be pi over 8. And how did you figure that out?
You just subtract pi from 7 pi over 8, and then you'd have to like multiply so the denominator, and then yeah, you
Yep.
get pi over 8.
Exactly that. Yeah, exactly that. So in order to find the related acute angle, to find the related acute angle, we notice that theta r, exactly what you said, Natalie. So here, let me put that back black here. So theta r equals pi minus 7 pi over 8, right? Because that's how you get this little segment here, right? That's where that little segment comes from. So pi minus 7 pi over 8. Again, we can think of pi as 8 pi over 8, just so the fractions are the same. Minus 7 pi over 8. So this ends up being just pi over 8. Okay, so that is the angle that's tucked away in here. So theta r equals pi over 8. Okay, and now we want to relate this back to the related acute angle. So we know that the related acute angle, like if we were to plot it, pi over 8 would be somewhere over here, right? Somewhere between 0 and 4 pi over 8, somewhere in quadrant 1, right? So this angle here is pi over 8. Now we are looking for sine of 7 pi over 8. So what can you tell me about sine in quadrant 2? Is sine positive or negative in quadrant 2?
Positive.
Positive, right? Good. And it's positive according to the CAST rule, right? So the CAST rule, C-A-S-T. So sine is both positive. Sine is positive in both quadrants 1 and quadrants 2. And so what that will tell us actually is that sine of 7 pi over 8 is equal to sine of pi over 8. And that's what it means by relating a trig expression back to its related acute angle. If they have the same related acute angle and they have the same sign, they end up being the exact same value. Okay. And so going back to our formula sheet here, that's kind of what this principal angles and related acute angles table is telling us, right? So here, we recognize that our principal angle was in quadrant 2, right? That was 7 pi over 8 was in quadrant 2. And then what we did is we related that back to sine of theta. So we recognize that sine of pi minus theta, that was calculating our related acute angle right there, was equal to pi over 8, and that's what sine theta is equal to. So we were able to relate these two to each other, okay? So this table kind of incorporates what we're chatting about here. I'm personally a visual guy, right? I always like to plot the angles and figure out where the related acute angle is located. That's just kind of my style, just because I like to look at things. But we can use Wolfram Alpha to check as well, right? So sine 7 pi over 8, we'll see if it's equal to sine of pi over 8. Hopefully it's true. It is true. These two expressions are equal to each other. Okay. Any questions about that type of example?
So like basically all you have to do is like find the that like related angle, and then that's just your answer.
Yeah. So well, there's kind of two parts for this. It's part one is find the related acute angle. And then part two is check the signs using CAS rule. That's pretty much it. So check signs using CAS. So for the second step here, we know that sine is positive in both quadrant 1 and quadrant 2. So we didn't really have to worry about that. Let's do another example where we do have to worry about the sign. Okay, so let's try to find one here. Let's try this one. So cosine of 13 pi over 12. All right, but same idea. Let's give it a go. So B, we have cosine of 13 pi over 12. Okay, so again, I'm going to do a quick sketch of this. This time, my denominator is 12, so I still have 0 over here. Pi over 2. Again, I want to think about this not as pi over 2. I want to think about this as like 6 pi over 12. And then I have pi. But again, I'm going to think about this as 12 pi over 12, because that's what my denominator is. And then I have 3 pi over 2. That's 270 degrees down at the bottom there. And I'm going to think about this as 18 pi over 12. Okay. So I've just converted everything to have the same denominator, just to help me figure out what quadrant this thing is located in. So our angle is 13 pi over 12. So in that case, we're going to be in quadrant 3, right? Because 13 pi over 12 is just a little bit bigger than 12 pi over 12. So our angle is going to be tucked in here. This is 13 pi over 12. Now, what's the related acute angle going to be in this case?
5 pi over 12.
Not 5 pi over 12, because careful, you never measure to the y-axis. You always measure back to the x-axis.
Oh, so it's going to be just pi over 12.
Very good. Yeah, exactly. So Natalie, I think you were trying to measure like this angle in here, right? Like this angle here. Yeah, so we just have to be careful on that part. But yeah, so our related acute angle, I'll plot that in green, is just this angle in here. And to find that related acute angle in this case, we notice that the related acute angle would be found by doing our angle minus pi, right? So in this case, our related acute angle will be 13 pi over 12 minus pi. So that's 13 pi over 12 minus 12 pi over 12, finding a common denominator. And that just ends up being pi over 12. So my related acute angle is pi over 12.
Sir, I have a question.
Yeah.
So when we're talking about related acute angles, it's always the angle on top of the line, you know what I mean?
The related acute angle, so let me draw So let's say if let's plot 4 different angles, 1 in each quadrant, right? So let's call this like theta 1, let's say. Theta 2 is here. Theta 3 is here. Whoops. Theta 4 is here. So in this case, our related acute angle for theta 1 would be right in here, right? There's our related acute angle for theta 1. This would be our related acute angle for theta 2. This would be our related acute angle for theta 3. And this would be our related acute angle for theta 4.
That's how it'll always be.
That is how it will always be. So like theta R1, theta R2, theta R3, theta R4. Does that make sense, Aiden?
Yeah, that makes full sense.
Okay, cool. So you're always measuring back to the x-axis. So Natalie, you tried to measure to the y-axis. It's always referred back to the x-axis. Okay. Now let's get back to this problem. Cosine pi over, or 3 pi over 12, 13 pi over 12, sorry. We know that's in quadrant 3. Is cosine positive or negative in quadrant 3?
Cosine in where?
In quadrant 3, so in this quadrant here.
It's negative.
Yeah, it's negative, right? According to our CAST rule, we're in the t quadrant, so cosine and sine are both negative. So in this case, this number is going to be negative. But we want to relate this back to our related acute angle, right? So we plot this angle here, this angle is pi over 12, right? So they have the same related acute angle. But if the angle is in quadrant 1, we know cosine would be positive there, which means cosine 13 pi over 12 and cosine pi over 12, those are going to have 2 different signs, right? Cosine 13 pi over 12 will be negative, but cosine pi over 12 will be positive. So that means when we make our final statement here, we know that this will have some relation to cosine pi over 12, but because cosine pi over 12 is a positive number, and cosine 13 pi over 12 is a negative number, we have to stick a negative in front of cosine pi over 12, right? Because we know that those signs won't match up. So again, if I come to Wolfram alpha just to check what I just said there, so if I have cosine of 13 pi over 12, let's just check if it's equal to cosine pi over 12. So without that negative sign. So I set up that statement and I get a result of false, which tells me that those 2 numbers aren't equal to each other. However, if I throw a negative sign in there, negative cosine pi over 12, I get a true because the number is the same. It's just that the signs were flipped because I didn't take into account CAST. But when I throw the negative sign in there, then everything kind of works out, right? Does that make sense for you guys?
Yeah.
Okay, cool. Let's try one from, I know this is going a little bit slow. I just wanted to kind of really spell out a few different types of questions for you guys. Let's give 7 a try. Oh, these are just true false statements. So this stuff is more like looking at properties of sine and cosine and properties of like these different kinds of properties and then determining if something's true or false. So maybe I'll leave that one to you guys. I mean, Wolfram alpha will obviously tell that for you if you want to check your answers. The back of the book obviously has the answers, but like part A, the way that I would justify part A is I would say, well, cosine has a period of 2 pi. So if I just add 2 pi to my angles, I end up back at the same part of my graph that I started at, right? So this statement is true because cosine is periodic over a period of 2 pi. So stuff like that, right? Sine of pi minus theta. Well, the way that you would do this, let's try that one together just really quickly, and then I'll leave the rest for you. So 7b, we're trying to show if sine of pi minus theta is equal to negative sine of theta. Okay. So I don't know what quadrant this is in, which means I can't use any of these like principal angle properties here. Sine of pi minus theta. So, I mean, is this, I don't think this is going to be true. The reason being, I mean, if, I know that sine of pi minus theta, how would I answer this?
Wouldn't you just like check these back to your formulas, and if it's not like there, you would say it was false?
Yeah,
Exactly.
that is pretty much what we're doing. Yes.
Is there like a way to solve for it or no?
I mean, technically there is. So what we could do, and now this is getting into the double angle formulas or compound angle formulas that we discussed. The way that we could do this one, I mean, easily, is we could use a compound angle formula here. Compound angle formula. So this is almost like working it like a trig identity, right? So we sort of set it up like a left-hand side, right-hand side check. Because really, this is a trig identity. We're trying to see if the left side is equal to the right side. So let's try to set it up like a trig identity. And then I'll use this compound angle formula. Because I recognize that on my left-hand side, I have sine of something minus something else. So that strikes me, oh, I can use a compound angle formula here. So let's apply this angle, this compound angle formula. So this is saying that sine of a minus b equals sine a cosine of b minus sine b cosine of a. Okay. So in this case, my a is pi and my b is theta. So let's apply that formula. So the left side is equal to sine of a, which is pi, cosine of b, which is theta, minus sine of b, so sine of theta, times cosine of pi. Okay, and then we just have to evaluate each of these. So off the top of your head, does anyone know what sine of pi is, or sine of 180?
Isn't it 90?
Not 90.
1.
Not one. Not one. Because sine,
Zero?
it's going to be 0. Yeah, because sine starts at 0, and then goes up to 1 at pi over 2, then back to 0 at pi, then negative 1 at 3 pi over 2, back to 0 at 2 pi, right? So when you're evaluating these, you want to have an idea of what the graph looks like, right? Okay, so we know that sine of pi is equal to 0. How about cosine of pi? Does anyone know what cosine of pi is equal to?
Isn't that one?
Not, cosine starts at 1 at 0. Then it comes down. So then at pi over 2, cosine is equal to 0. And then at pi, it's still going down. It dips all the way down to negative 1. And then it comes back up. Does that make sense? So cosine pi is equal to negative 1. And so this expression, the way that it works out, the first term is gone, right? Because 0 times cosine theta is just 0. So we get 0 minus sine theta times negative 1. Well, sine theta, or minus sine times negative 1, that's just going to be positive sine theta. So this expression is equal to sine of theta. But then we were trying to see if this thing is equal to negative sine of theta. So is this statement true? Statement is not true, right? Because we found that sine of pi minus theta was equal to positive sine theta, not negative sine theta. And again, if we go to Wolfram alpha and we just verify this, sine of pi minus x equals equals negative sine of x. If we try to set that up, we're going to end up getting, okay, this is a little bit strange because there are points where that statement is true, but it's not true for every value of x. However, if we do sine pi minus x equals sine of x, we can see we get a true statement, right? Meaning it's true everywhere, over every value of x. sine pi minus x is true some places, but not every place. And so that's where we have to be a little bit careful. So that's what you want to do for those kinds of questions, for question 7 there. Showing that something's true and false. It's almost like a mini trig identity problem, really, at the end of the day. How do you guys feel about that one?
Pretty good.
Pretty good? Aiden, how about you?
Yeah, it's not bad.
Not bad? Ava, I just saw you that you got back on. How do you feel about this true false type questions?
Like I have to look at it more because my phone kind of just like completely lagged out. That's why I left.
Okay.
So yeah.
Okay, no problem. I mean, there's I only went through A and B, so there's definitely more practice there. So if you want to give it a try and see if it kind of clicks together, but yeah, essentially these are kind of like trig identity problems, right? You want to treat them sort of like trig identity problems when you're showing. Okay, let's try 7.2. So let me just go to my, so the homework for 7.2. Do you guys find this useful? Is this helpful for you guys?
Yeah, for sure.
Especially.
Okay, awesome. I wanted to like go a bit slow today just to make sure everyone was kind of back on the same page. Let's try 7.2 here. So 7.2 is all about the compound angle formula, which we've already seen one instance of today, but we'll give a bit more practice here. So 1, 3, D and F, 4, C, D, F, 5, 6, 8, C, F, and 9. So we definitely won't get through all of these. Let's try a couple at least, and then we can go on to some, I guess, double angle formula, and we'll practice some trig identities as well. So yeah, 1. Okay, I'll do A with you guys. So rewrite each expression as a single trigonomic ratio. So I'll do 1A with you. This actually isn't so bad, but again, you kind of have to recognize the pattern here. So with this question, we have sine of A, cosine of 2A, and then plus cosine of A, sine of 2A. Okay, so our goal is to kind of simplify this a little bit, right? Right now, this expression is kind of complicated looking, so let's try to make it simpler. So looking at our compound angle formulas, let me get rid of that bar. There we go, that's a lot better. So looking at our compound angle formulas here, and looking at this pattern, so we have a sine, cos, plus cosine. Does that match up with any of these 3 formulas here?
Not like, actually, it matches kind of with the first one.
Yeah, sine of A plus B, right?
Yeah.
Now, of course, this is like A and 2A. It's not the exact same, but the pattern is the same, and that's what the most important part is. Okay, so really, we're trying to relate this back to, we know that sine A plus B equals sine A cosine B plus sine B cos A. And we can kind of complete this pattern by recognizing, well, A and 2A, those are kind of serving like our A and our B values in the formula itself, right? So that's the kind of pattern matching that we're doing. So we can boil this down. We know that this is equal to sine of A plus 2A. So this entire expression is equal to sine of 3A. And then we're done. But obviously, sine of 3A is a lot simpler than that big, long expression, right? So this is how these trig identities work in practice. You have something that looks complicated and you want to make it simpler, or you have something fairly simple that you can't evaluate right away, so you make it more complicated so that you can make it simpler. Okay, that's kind of how these work.
Wait, so what happened to the cosines though?
Well, again, what we're recognizing here is that, let me kind of use my highlighters to my advantage here. Let me just erase what's there currently. So the idea here, Natalie, is I recognize that I have a sine A, I have a cos 2A, cos B, right? So those pieces match up together. I have a cos A, and I have a sine b, sine 2x, right? So I recognize that I have a similar pattern going on here, okay? Now, when I recognize that pattern, what I'm ultimately going to do is I'm going to replace that entire pattern with something that looks like sine of a plus b. Once I recognize what sine of, or what the a and the b values are in that pattern, okay? And so I just replace it with a single term. It's kind of like I have the right-hand side of this equation, and I'm going to replace it with the left-hand side of the compound angle formula to make it simpler, okay? This is kind of like, I mean, you guys have done pattern matching in the past, right? Like if I have something like a squared minus b squared, you look at that and say, oh, well, that's a difference of squares. So I know that I'm going to replace this with a minus b, a plus b, right? Or, I mean, so the way that that might work is, okay, let's say you have x minus 5, x plus 5. Well, I look at that, I'm like, oh, well, that is the difference of square formula, but just in reverse. So if I want to expand this out, I know instantly that this will be x squared minus 25, right? So it's all about pattern matching and converting one side of a formula, one side of an equation that you know to another side, because that might tell you more information or it might make it simpler, okay? So is that a bit more clear how I just replaced all of those sines and cosines with just one single sign?
Yeah.
Excellent. Aiden, how do you feel about that little pattern matching exercise there?
Yeah, that makes more sense.
Okay, excellent. Let's try another one that's a little bit more concrete that deals with numbers. So let's see, this 3. 3 is important. Let me show you what 3a is referring to, just so you guys can see it. Now 3a is in degrees, so it's a little bit different, but express each angle as a compound angle using a pair of angles from special triangles. So what this is telling you to do is, we know that 75 degrees does not appear in any of our triangles, any of our special triangles. So what we want to do there is write this as, say, like 45 degrees plus 30 degrees, because both 45 and 30 are part of our special triangles. And then we can use that and apply our compound angle formulas from that, depending on if we're taking like sine of that angle or cosine of that angle or what have you, okay? So that's an example of, notice that I only assigned 3 D and F for this one, because those are angles in radian measure. So obviously we're going to be working in radians, but this is same idea with degrees, right? So your job would be to turn pi over 12 into either 2 angles added together or 2 angles subtracted from each other. But both of those angles would appear in a special triangle, okay? So that's the idea behind 3. Now looking through here, let's try 1 from 4, because 4 is how you kind of do this stuff in practice. So determine the exact value of each trig ratio. Let's try 4, I think I only assigned a couple here. Let's try 4c together. So 4c states that I have tan of 5 pi over 12. Now, looking at 5 pi over 12, does that appear anywhere in any of my special triangles? Do I have pi over 12 in any of my triangles?
No.
No, right? I have pi over 4, pi over 3, and pi over 6. So pi over 12 is a no-go. I don't want to work with that. And so what I need to do is I need to find a way to split up 5 pi over 12 into either 2 angles added together that are part of my special triangles, or 2 angles subtracted from each other that are part of my special triangles, okay? So let's think about this. Can anyone spot, say, 2 angles that add up together that get you 5 pi over 12, but these angles are some combination of, say, like a something pi over 6, or something pi over 4, or something pi over 3? Can anyone spot what angles might work there?
You could do pi over 6, or yeah, pi over 6, and then you could like multiply that to make it like a 12 denominator.
You're right. Yep.
And then add it with like
would become 2 pi over 12.
2 pi over
Yeah.
12. Yeah, exactly that. Yeah. So like that's a good 2 pi over 12, which is pi over 6. That's what you were saying, Natalie. Great. I agree with that. So if one of those angles is 2 pi over 12, which is pi over 6, what would the other angle have to be?
Something 3, I guess.
3, exactly.
Yeah,
right?
3 pi over 12, yeah.
And 3 over 12, what is that as a fraction?
1 over 4.
Perfect. So
Yeah.
pi over 4, right? And so just like that, I've turned this single angle, 5 pi over 12, into adding up two angles that are both part of special triangles, right? So really, instead of writing tan of 5 pi over 12, which is problematic because I don't have any special triangles going on there, instead we can write this as tan of pi over 4 plus pi over 6, because I know that those two angles add up to give me 5 pi over 12. All right, are you guys with me here so far? Is this good?
Yeah.
Yeah.
Excellent. Now I recognize that I have tan of two angles added up together. And so right there, that tells me, okay, I must have some sort of compound angle formula to apply. So let's apply that formula, and then let's see what happens from there. So let's go to our formula sheet. And indeed, we recognize that we have a formula for that, right? So we use the expression tan of A plus B equals. Now, when we're dealing with this identity, all you have to do is make sure that you're not mixing up the positives and negatives. So in this case, I will have tan of A plus tan of B over, and then my denominator, I will have 1 minus, because notice here, this is inside the brackets on the left side is a plus minus. The sign in the denominator here is a minus plus. So we have to split the signs there, but then we'll have tan A, tan B. So we're going to be applying this formula. So tan of pi over 4 plus pi over 6 equals tan of pi over 4 plus tan of pi over 6 over 1 minus tan of pi over 4 tan of pi over 6. Okay. Now my job here is to figure out what tan of pi over 4 and tan of pi over 6 are equal to. Okay. And so to do that, I go to my special triangles, right? So let's pop open the special triangles here. So my first one, I have pi over 4, 1, 1, root 2. And my second one, I have pi over 6, pi over 3, 1, root 3, and 2. So who can help me out here? What is tan of pi over 4 equal to?
Is it just 1?
Just 1, yep. And then Aiden, what's tan of pi over 6 equal to?
Tan of pi over 6. Like as a number?
Yeah, using like SOHCAHTOA and this special triangle.
Oh, what do you mean? Like using the ratios?
Yep, trig ratios, yeah. So like tan is opposite over adjacent, right?
Yeah. So it'd be 1 over square root 3.
Excellent, good job. Nice. So we have tan of pi over 4 and tan of pi over 6. Now what we can do is plug those into the formula wherever we see tan of pi over 4 or tan of pi over 6. Okay, so we're replacing the trig expressions with their actual ratios now. So this is all in a step to figure out like an exact value for this expression, right? So let's plug in here. So tan of pi over 4, that's 1, plus tan of pi over 6, that's 1 over root 3, divided by 1 minus tan pi over 4, that's 1. Tan pi over 6 is 1 over root of 3. And then we just try to simplify this expression, right? So we have 1 plus 1 over root of 3. That's kind of messy because I have a fraction within a fraction, but we'll deal with that. We'll try to figure that out in a second. Over, then I have 1 minus 1 times 1 over root 3, so that's 1 over root 3. And again, that's kind of messy, right? Because it is a fraction within a fraction. So what I can do here, technically at this stage, I'm pretty much done, right? I found an expression. Now, like if I were acting in like my physicist brain, I would say that's good enough. I don't really care. You can turn this into a decimal for all that, right? I don't really care if there's an exact value. But in mathematics, usually you have to be a little bit careful with that, right? We don't want fractions within fractions. We don't want radicals in the denominator, stuff like that, like proper form. And so what we can do here is find a common denominator for both the numerator and the denominator. So in this case, I will have like root 3 over root 3 plus 1 over root 3. And then in the denominator, I will have root 3 over root 3 minus 1 over root 3. So I found a common denominator. In both of them, it's root 3 is my common denominator. And then I can just simplify this a little bit, right? So I have root 3 plus 1 over root 3. That's my numerator. And I have root 3 minus 1 over root 3. And that's my denominator. And what's really cool is that both the numerator and the denominator, I have a fraction within a fraction, right? But in both of those, I have root 3 in the denominator. And so I can just cancel those out. It's a nice simple cancellation. And so I'm left with root 3 plus 1 over root 3 minus 1. And then at that stage, I'd say that's good enough, right? But even like, even going back to this line right here, that is the correct answer, right? That is an exact value of the trig expression. So if you get that far, then you'll get the majority of the marks in the question. There might just be like, say, one thinking mark to get it simplified down to like a nice value, right? But that's all grade 11 material, right? Working with radicals and simplifying radical expressions. That's one chapter of grade 11, I think. Pretty sure. Should have been, if not. So that's a really important type of question, right? Taking an expression, so tan of 5 pi over 12, there was no trig identity, or there was no special triangle for that. And so we had to use some sort of trig identity. We recognize that we can split the 5 pi over 12 into two angles that were part of the special triangle, and then just kind of carry through the formula until we could find an exact value. Right? Any questions about that example?
No, it seems like long, but
it's a lot of algebra, I guess, right? Really the hardest part is this first line here, like figuring out how to split up the angles. Once you get that, then you're kind of just letting it carry you through, right? Evaluating each part, special triangles, all that. But that's all kind of trig review by this point, right? Okay, shall we try one or two more? Let's see what other questions we had. Where were we? So 4, let's just see if there's some good ones. 4, we did. 5. Yeah, 5 is another, like applying trig identities, so, or applying the angle formulas. So this one we don't have to, I mean, maybe we could try one of them. 5 and 6 are kind of the same. 8, C and F, also kind of the same. Let's try 1 of 6, so, or maybe 1 of 5. So let's try 5F together, shall we? So 5, oops. Again, this is kind of just some pattern matching here. So 5F, we're trying to simplify cosine of pi over 2 plus pi over 3. So in this type of example, this one's almost easier, right? Because you already get the two angles, they're already separated. All you have to do is apply the compound angle formula. That's it. So let's go to our compound angle formulas. Here we recognize that we're going to be applying this formula. So the formula that we need, cosine of A plus B equals, so we have cosine A, cosine B minus, so we have to be careful about the signs here. Notice that inside the brackets is a plus minus sign on the left-hand side, but then on the right-hand side, it's a minus plus sign. So that tells you to use the opposite sign. So cosine A, cosine B minus sine of A, sine of B. Okay. And then we just,
So,
oh yeah, go ahead.
sorry, so you do the opposite of whatever was in the first bracket for that one?
Exactly, yes,
Okay.
yes. So yeah, paying attention to the plus minus signs is important, right? If you have a plus minus sign on the left-hand side and a plus minus sign on the right-hand side, that just tells you to use the exact same sign, right? But if you have a plus minus sign on the left side and a minus plus sign on the right side, that tells you to flip it. So in our case, we have a plus sign on the cosine A plus B. So on the right side, we use a minus sign. So we have to remember to flip that. So let's give this a try. So cosine of pi over 2 plus pi over 3 equals cosine pi over 2 cosine pi over 3 minus sine pi over 2 sine pi over 3. We can do some nice simplification just by recognizing the graphs here. So for cosine, starts at a max, comes to a min. So cosine pi over 2 is 0. And for sine, again, we can use the graphs to help us out here. So sine starts at a min, or starts at the midline, goes to a maximum. So sine pi over 2 is equal to 1. Okay, and so we can simplify this quite immediately. The first term is gone, right? So cosine pi over 2 times cosine pi over 3, that's 0 because cosine pi over 2 is equal to 0. And so this ends up being negative sine pi over 2 is 1 times sine pi over 3. And sine pi over 3, we can use a special triangle for that. So let me just copy my special triangle here, bring it down.
Wait, so how did you cross out the cos stuff?
Because cosine pi over 2 is equal to 0.
Oh, okay.
So that entire term is just gone, right? But sine pi over 2 is 1, so that term will stick around. We'll still have that. And then lastly, we need sine pi over 3. So for that, we come to our special triangle, opposite over hypotenuse. So that's going to be root 3 over 2. So this is negative 1 times root 3 over 2. So just negative root 3 over 2. And that is our final answer. Any questions about that example?
No.
So, like, basically you just find whatever one works and then use, like, the special triangles to find what it equals, I guess?
Exactly. Pattern matching and then special triangles. That's it.
Okay.
Yeah, it's not too hard.
Not too bad. Nice. Let's see what the other examples are for this homework. But it seems like we're kind of getting the hang of this part here, so we might not belabor this anymore. 6 is the exact same as that. 7 is the same, but with 7, you have to worry about figuring out how to split it up, right? So I didn't assign A and B, but like 11 pi over 12. Well, I can rewrite that as, say, 9 pi over 12 plus 2 pi over 12, and that would get me 2 special triangles, right? 13 pi over 12, I can write that as 9 pi over 12 plus 4 pi over 12, right? So the trick with these ones is just figuring out a clever way of splitting up whatever your angle is into 2 other angles that are special triangles, right? So these questions are a little bit harder because you have to figure out the division, but other than that, they're the same as what we have been doing. So that's 8, and then number 9. Okay, number 9 is actually really interesting. I like number 9. Let's give it a go. Okay. We've done a couple questions kind of like this. These ones are harder than the ones that we have been doing. So let's really focus here. So number 9 is telling us that sine of x equals 4/5. So we don't know what the angle is. We just know that trig ratio is equal to 4/5. And we also know that sine of y is equal to -12/13. And now this part in here is kind of confusing, like especially the first time you see it. So it's saying that x is between 0 and pi/2. Now, all that's telling you is that x is in the first quadrant. That's it. There's nothing really special going on there, just x is in the first quadrant. So let's kind of make a little picture to help us out there. So we're told that x is between 0 and pi/2. So there is x. And we also know that x is equal to 4/5. So that's like the opposite over the hypotenuse is 4 and 5. So we can turn that into a little triangle, right? Just by recognizing, or because we're told that x is between 0 and pi/2. Now y, we're told that y is between 3 pi/2 and 2 pi. So that means y is in quadrant 4, right? Because 3 pi/2 is at the bottom. 2 pi is once we've gone all the way around. So y is somewhere in quadrant 4. So let's draw that out here. So this is y. It's our angle y. It's in quadrant 4. And this ratio is 12/13. Okay. So that's the triangle that we would draw for y. And we know where to draw it again because y is between 3 pi/2, which is down here, and 2 pi, which is 1 full rotation, so we're back to the positive x-axis. So that's how we can tell where those angles are. Okay. Now, so given both of those, our job is to evaluate cosine of x plus y. Okay, so this is kind of a tall order for us, but let's give it a go. Let's try to figure out how to work this. So I'm looking for cosine of x plus y. The first thing that I'm going to do here is apply a compound angle formula. So I know that cosine of x plus y is equal to, let's go back here, equals cosine x, cosine y, minus sine x, sine y. Okay. And so I already know 2 of these things, right? I know that sine x is equal to 4/5. So I already know what that is. And I know that sine y is equal to -12/13. So I know what sine y is equal to. But I have no idea what cosine of x, I have no idea what cosine of x or cosine of y are equal to. So cosine of x, I'm still in the dark there. Cosine of y, I also don't know what's going on with that. Okay. So my job right now is to figure out an expression for cosine of x and cosine of y, and then I can evaluate what this entire big expression is equal to, right? So let's try to figure out cosine of x first. So with cosine of x, I come back up to my picture here. Well, I already know the hypotenuse, right? So that's one good first step here. I know the hypotenuse, but I don't know what my adjacent side is. So how am I going to find the adjacent side here? What's the plan?
You use like Pythagorean.
Pythagorean theorem. Yep. We've done a couple questions like this at this point, right? Kind of similar problems to this. So let's use Pythagorean theorem to find this this third side length here. So we know that 5 squared is equal to, I'll call this b just for these purposes, 4 squared plus b squared. So 25 equals 16 plus b squared. B squared is equal to 9, so b is equal to 3. So that means that cosine of x, Aiden, what's cosine of x going to be equal to then?
Pardon me?
What is cosine x going to be equal to now that we found this this adjacent side?
Oh, 3/4.
Not 3/4, careful. Adjacent over hypotenuse.
Oh, 3/5.
3/5, there we go, nice. You found cotan, not cosine.
Yeah.
So, okay, there we go. So we know that this is 3/5. That's good. Now let's do the exact same thing, but for our angle y. Okay, so exact same idea. I'm looking for this side length here. So that's my unknown side. Again, I'm going to call that b. And again, I'm going to use Pythagorean theorem to solve for this, right? So 13 squared equals 12 squared plus b squared. I'm going to use my calculator for these. 13 squared minus 12 squared. So b squared is equal to 25. So b is equal to 5. Natalie, what's cosine of y going to be equal to then?
5/13.
Very good. Yep. And so cosine of y is 5/13. I already knew what sine of x and sine of y were, right? So sine of x is 4/5, and sine of y was negative 12/13. And then I'm all set, right? I have, this is just a number times a number minus another number times another number. So I just multiply, collect like terms, or find a common denominator, and I'm done. So 3/5, that's 15/5 times 13. So that's 15, let me make that a little bit nicer. 15/65 minus, so I have 4 times negative 12. So minus negative 48/65 again. So that'll be 15 plus 48 because I have a negative times a negative. So this will be equal to 63/65. And that's what cosine of x plus y is. So kind of an interesting sort of outside the box example, right? You're given some information. You have to use that information to find other pieces of information. And then you apply some sort of formula to get what you need. Okay. How is that exercise there?
Made things a little easier.
Yeah.
Cool. Okay. The other parts of that question here, they're all kind of the same, except you're asked to find a different type of expression. So the fact that we already have these triangles figured out, that'll make the rest of these exercises quite a bit easier, because then you just read off the triangle what each of the ratios are. So the rest of those aren't going to be so bad. Okay, how are we feeling? Do you guys want to take a little break and then kind of keep going with a few more of these exercises? Would that be helpful? I know we're going a bit long today, but what do you guys think?
Sure, that works.
That works? Sure. Awesome. Okay, so let's take 10. So let's come back at 12:21, okay? And then we'll keep going with this stuff. All right, are we back? Hello, hello,
Yep.
back. Aiden, how about you? Are you here?
Yeah, I'm here.
Here. Ava, are you here?
Yeah, I'm here.
You're here. Lovely. Excellent. Okay, let's try a few more problems. Yeah, sorry for taking you guys so long, but I figure it's kind of nice to have these days every once in a while, right? Just like solve some problems.
Yeah, it's helpful.
Helpful. Awesome. Okay, we'll try to do this more down the stretch, especially with like the final assessments coming into play, and like I'm down to take a bit more time to sit with you guys and just work through problems. That's my favorite thing to do, is just like work through problems, you know. Okay, so let's try a few more. Now we're getting into the double angle formula stuff. So these are kind of really similar to the compound angle formulas. So if we compare the compound angle formulas to the double angle formulas, again, it's a lot of pattern matching. That's pretty much it. So let's try some of these. So let's go through 1a together. So 1a says we have 2 sine of 5x cosine of 5x. So let's go to our formula sheet. 2 sine 5x times cosine 5x. Does that match up with any of these formulas here? Any of the double angle formulas?
No.
I mean, not exactly, but the pattern of it doesn't match up with like the rough pattern of this formula.
The top one, I guess.
Yeah, right. So comparing these, we know that 2 sine theta cosine theta is equal to sine of 2 theta, right? And so we can recognize some similarities, right? If we kind of equate 5x and theta, we can see that those two expressions kind of roughly match up to each other, right? So in this case, this is equal to, this thing we can replace with sine of 2 times 5x. So sine 10x. Okay. So again, the idea there is we took something that looked kind of complicated, we recognized that it followed a certain pattern, and we made it simpler. And that's it. Okay. Let's try another one. Let's try 2e together. Okay, so 2e. Similar kind of problem, but now we're actually given an angle. In problem 1, we were just given a variable, or 5x, right? Some variable expression. So let's try 2e. So 2e, we have 1 minus 2 sine squared 3 pi over 8. 3 pi over 8. Again, we look at this and we're like, well, 3 pi over 8 is not a special triangle, so we can't evaluate this directly. So for that, what we want to do is we go to our formula sheet and we compare this expression to the double angle formulas that we have. Does anyone notice one that might work here? What this thing could be equal to? So I look at this and I say, well, I have 1 minus 2 sine squared of something. I also recognize that that formula appears here, right? Cosine 2 theta is equal to 1 minus 2 sine squared theta. So I'm going to be applying that formula. So I know that cosine 2 theta equals 1 minus 2 sine squared theta. Okay, so in this case, I'm given the right-hand side of the equation, and so I can convert that to the left-hand side. All I have to do is recognize that in this example, my angle, my theta value, is equal to 3 pi over 8, and then I can apply this formula, okay? So in this case, I know that 1 minus 2 sine squared of 3 pi over 8 is equal to cosine of 2 times 3 pi over 8. So if I have applied my double angle formula there. And then cosine of 2 times 3 pi over 8. So for that, this is cosine of 6 pi over 8. But I can reduce that. That's cosine of 3 pi over 4. Okay, so going back to the question here, I've evaluated, or I've expressed this as a single trig ratio, right? So cosine 3 pi over 4 is a single trig ratio. But now I have to evaluate it. So I want to find a number that this thing is equal to, okay? So for that, I recognize, oh, 3 pi over 4. Now that I can use a special triangle for. So now I'm going to go through my process of actually figuring out what this is equal to. So 3 pi over 4. Again, I like to draw it out. You don't have to do this every time. I just find it helpful. So pi over 2 is 2 pi over 4. Pi is 4 pi over 4. So that means 3 pi over 4 is right in here. So 3 pi over 4 is in there. I know that my related acute angle, so between 3 pi over 4 and 4 pi over 4, my related acute angle, theta r, is just pi over 4. So cosine of pi over 4, I can use a special triangle for that. So let me just scroll all the way up to grab my special triangle, and then I'll bring it back down. There we go. So for cosine pi over 4, I know that I can use this special triangle. So I know that cosine pi over 4 is 1 over root 2. And so I'm not looking for cosine pi over 4, though. I'm looking for cosine 3 pi over 4. So the only thing I have to do now is just make sure that I'm following with the cast rule, right? So in this case, I'm in quadrant 2. Is cosine positive or negative in quadrant 2?
Negative.
Yep, negative. So that means cosine 3 pi over 4 is equal to negative 1 over root 2. And then I'm done. Okay. And of course, I can check this, right? If I go back to Wolfram alpha, I just can type in 1 minus 2 sine squared 3 pi over 8. And ideally, I'll get negative 1 over root 2 as my answer. It's thinking about it, it's thinking about it, gives you an approximation, and it gives you an exact value of negative 1 over root 2. So again, the cool thing about these double angle formulas, or even the compound angle formulas as well, we have an expression that we can't evaluate directly, but we can use a formula, we can use one of these trig identities to convert this into something that we can evaluate, and then we can actually go through and figure out the answer, okay? Any questions about that example?
Seems to make sense.
Makes sense, cool. Aiden and Ava, are you good with this type of exercise here?
Yeah, I think so.
Okay, hopefully you're seeing a trend though, right? It is a lot of like recognizing patterns, applying formulas, and whatnot, right? Okay, let's try 1 or 2 more from this section, then we'll try a couple trig identities, and then we'll be done for the day. I know I'm keeping you guys long, but again, I want to make sure to cover a few different types of questions here. So 4, 5, 6, 7 are all kind of the same. So let's try at least some of 7, shall we? So 7, what it's saying is that we have to determine the values of sine 2 theta, cosine 2 theta, and tan 2 theta, knowing that cosine theta is equal to negative 4 over 5. So we're told that cosine theta equals negative 4 over 5. And we're also told some sort of constriction on what theta is equal to. So here it's saying that theta is between pi over 2 and pi. And what that really is saying is that this angle is located somewhere in quadrant 2, right? So this angle is located somewhere up here because pi over 2 is right here and pi is right here. So this is where our angle theta is located. Now, again, we can turn this into a triangle, right? We saw this kind of question when, I think 2 examples ago or something, where we have to kind of turn this into a triangle. We know it's cosine that we're dealing with, so we know our adjacent side is 4 and our hypotenuse is 5. And so let's actually figure out what our side length b is going to be. So we're going to use Pythagorean theorem. 5 squared equals 4 squared plus b squared. B squared is going to be equal to 25 minus 16. B squared is 9. B is 3. So we found our side length B. And this is actually going to tell us what sine and tan are going to be, as well as cosine. So we already have a value for cosine. We know that cosine is -4/5. Who wants to help me out with sine? What's sine theta going to be equal to?
Opposite over hypotenuse.
Good, yeah. And so what's that going to give us for this triangle?
It'd be 4/5.
Careful, opposite. Our angle that we're referring to is in here.
Oh, so 3/5.
3/5, good. And because we're dealing with sine and we're in quadrant 2, is that going to be a positive 3/5 or a negative 3/5?
Positive.
Good, very good, excellent. Aiden, while you're here, do you want to help me out with what tan of theta is going to be?
So it'd be opposite over adjacent, so it'd be 3/4.
Awesome. And we're in quadrant 2, so is that going to be positive or negative?
It'd be negative.
Negative, very good, nice. So now we have our values for sine theta and tan theta. So now we know, and we already knew what cosine theta was, right? So we have cosine theta, we have sine theta, and we have tan theta. So now this question, we're trying to figure out what sine 2 theta, cosine 2 theta, and tan 2 theta are. So our job is not quite done yet. We want sine 2 theta, we want cosine 2 theta, and we want tan 2 theta.
When they say 2 theta, they mean 2 times the measure of that angle.
Exactly. But notice that we haven't calculated what the angle is, right? So for this, sine 2 theta, what we're going to do is we're going to use one of our double angle formulas. Okay. That way we don't have to figure out what the angle is. So let's go to our formula sheet here. We recognize that sine 2 theta is equal to 2 sine theta, cosine theta. Okay. Sine theta, we calculated, right? Sine theta was equal to 3/5. And cosine theta, that was given to us in the question. So this is going to be equal to 2 times sine theta, which is 3/5, times cosine theta, which is -4/5. Okay, so multiply all the numerators together. We have 2 times 3, that's 6, times -4 is -24 over 5 times 5, so -24 over 25. And so we figured out what sine 2 theta is equal to. Okay. And then we can repeat this process for cosine 2 theta. So cosine 2 theta, we actually have 3 different formulas that we can apply. Now, because we were given cosine theta in the question, I'm gonna choose this formula, right? Because there's a chance that I could have messed up my calculation for sine and tan. So let's stick with the things that were given in the question. So in this case, cosine 2 theta is equal to 2 cos squared theta minus 1. And cos squared theta, again, we know that from the question, right? So that's 2 times -4/5. But because it's cos squared, it's -4/5 squared minus 1. So that'll be 2 times 24/25, take away 1. Let me bump tan down a little bit here. So 2 times 24/25, so that's 48/25 minus 1. And 1, I'm going to convert that to 25/25, so I have a common denominator. 48 minus 25, that's 23. So this answer is 23/25. Okay. And then last but not least, let's evaluate tan 2 theta. So tan 2 theta, again, I'm going to apply this pattern. So we know that this is equal to 2 tan theta over 1 minus tan squared theta. And I have a value for tan theta, so I'm going to apply that here. So I have 2 times -3/4 over 1 minus -3/4 squared. So that is -6/4 in the numerator over 1 minus, now -3 squared is 9/16. So that'll be 1, we can write that as 16 over 16 minus 9 over 16. So that's going to be 7. So negative 6 over 4 over 7 over 16. Now, in this case, I'm dividing fractions. So I want to rewrite that. So I'm dividing by 7 over 16. So instead of writing it like that, let's multiply by 16 over 7. Because if I'm dividing fractions, you flip it, then multiply. So 6 times 16 is negative 96 over 4 times 7, which is 28. We can reduce that a little bit. So 96 over 2 is, that'd be 48 over 14. And we can go a little bit further than that. 48, so that's 24 over 7. And I think that's our final answer. So a little bit of a different example, right? Again, we're given one trig ratio. We're given cosine. We're told where the angle is. That lets us figure out the other trig ratios, sine and tan. And then from there, we just apply our double angle formulas. And that's it. Any questions about that example?
No.
Okay, let's, shall we try 1 or 2 trig identities maybe? And then we're done for the day? Okay, so I didn't go through, I mean, 4, 5, 6, 7, those are all kind of the same. I didn't go through 8, but 8 is kind of, yeah, I'll let you guys think about 8. That's more of a sort of a thinking kind of application style problem, so a little bit different. And then 10 and 11, those are kind of just sort of explanation questions. 11 is probably the harder one, so see if you guys can do it. Again, it's kind of pattern matching. Yeah, see if you guys can tackle that. Let's try some trig identities, shall we? So trig identities, page 417, number 8, 9, 10, and 11. Okay, yeah, these are all kind of a bit different, right? Trig identities are sort of hard to generalize, I guess. But let's try this, because every trig identity kind of has its own different method associated with it. So let's give 9a a try, and maybe you guys can kind of help me or guide me along with this. So with 9a, we have cos squared theta minus sine squared theta over cos squared theta plus sine theta cos theta. So that is our left-hand side. So I'm just going to write left-hand side here. And our right-hand side is equal to 1 minus tan of theta. Okay, this seems like a tall order here. What side would you guys start with in this case?
The left side.
Yeah, and why would you start with the left side?
Because it's really difficult.
Yeah, it's a little bit more complex, right?
Mm-hmm.
Now, the one thing that I recommend when doing trig identities is try not to like, I know when I was first learning this, my first gut instinct is like, okay, I'm going to go to the formula sheet and I'm going to see if there's a trig identity that works for this. In this case, I spot like cosine squared theta minus sine squared theta is cosine 2 theta. So I spot that. It turns out that I don't want to jump in and use that right away. That will actually mess me up quite a bit here. One thing I do recognize here, and this again requires a lot of pattern matching and seeing a lot of these. Here I have cos squared theta minus sine squared theta. What does that remind you of in terms of like factoring?
What do you mean?
That difference of squares thing?
It's a difference of squares. So Aiden, what I mean by that is like, you know, if we have a squared minus b squared, we can factor it, right?
Yeah,
A minus b times a plus b.
same sort of thing.
Same pattern, right?
Yeah.
And so what I'm going to do first, my first step here is going to be to actually factor, right? So this requires no knowledge of trig identities to begin with, right? All I'm doing is I'm factoring. So this is like a grade 10 concept. Obviously, it's harder because instead of A's and B's or X's and Y's, we're dealing with like trig expressions like sines and cosines. So definitely a little bit different, but we're still applying the same formula, the same pattern here. So cos squared minus sine squared, instead of having that, I'm going to write this as cos theta minus sine theta times cos theta plus sine theta. Okay. Now looking at the denominator here, again, I should check to see if I can factor something first, right? In this case, I recognize, well, I have a cosine squared theta in the first term of my denominator, and I have a cos theta in my second term of my denominator. And so I can do some common factoring, right? I can common factor out a cosine theta. So I'm going to
Mr.
factor.
Hopkins?
Yeah, go ahead.
Sorry, would it be bad if you had like canceled the cos squared theta? Like, couldn't you have done that?
I can't do that.
You can't.
Because the reason why I can't is because I'm adding and subtracting. So when you're adding and subtracting, you can't cancel.
Right.
Yes.
Right.
But
Okay.
keep that thought though, because we will be doing some canceling in the next step. Okay.
Okay.
So if I common factor out a cosine theta, then what I'm going to be left with is, well, cos squared. If I factor out a cos theta, then I'm going to be left with just cos theta. And then in my second term, I have sine theta cos theta. So I factor out a cos, and I'm left with just plus sine theta. Okay, now Natalie, what do you notice here?
Can you cancel? Oh, you can cancel the cos plus sine, and the other one. Yeah.
Exactly. And we can do that because we're multiplying. So when you're adding and subtracting, cannot cancel. However, when you are multiplying, when we have an entire term that's common in both the numerator and denominator, then we can cancel. Okay. So in this case, we can cancel out cos plus sine. So cosine theta plus sine theta, those are gone. And we're just left with cosine theta minus sine theta over cosine theta. Okay. Now, at this stage, I'm kind of stuck, right? Like I'm not actually stuck, but looking at it, I'm kind of like, okay, I can't really factor. I've already factored. I've already simplified this thing. It's getting pretty close. Let me look at my right-hand side to see what I need to be ending up with, right? So on the right-hand side, it's relatively simple. I have 1 minus tan theta. Okay, so let's actually play around with the right-hand side a little bit. So I know that tan theta is equal to sine theta over cosine theta. Okay, so that looks pretty good. Well, here I'm subtracting two fractions, right? So why not find a common denominator? So let's try to find a common denominator here. So in this case, that'll be cosine theta. So I have cos theta over cosine theta minus sine theta over cosine theta. And then I have my common denominator, so I just subtract away the numerator. So cos theta minus sine theta over cosine theta. And I matched it up, okay? So even though these are called trig identities, really, we only ended up applying a single trig identity here, right? We turned tan theta into sine theta over cosine theta. The rest of it was just algebraic manipulation, cancellation, finding common denominators. So a lot of algebraic skills, but we're not really using these formulas, this formula sheet at all. I mean, we are, but very, very limited, in a very limited way, right? Any questions about this trig identity here?
No.
Okay. Kind of tricky, right? Again, always check to see like what kind of operations you can do. Shall we try one or two more?
Sure.
Okay. Let's try 9C here. I'm just picking these at random. Every question kind of has a different structure to it.
So is this like, is that like the level of difficulty that would be on our tests?
Yes.
Right.
Yes, it will be. Yeah.
Okay.
Now let me actually quickly check. Actually, I have it over on my other monitor here. I think on the test, so again, the test next week, I think Monday or Tuesday, we'll kind of make a decision tomorrow on that. On this test, there are 2 trig identities. Now, for these 2 trig identities, I realize that sometimes it is a challenge to kind of do these on the fly. So they're both worth 3 thinking marks. So if you feel like you get stuck and you don't know how to progress, I will give you a hint, but it'll cost you 1 point. All right. So that'll be how the trig identities are structured on the test. Does that seem pretty fair?
Yep.
Cool. Okay. So you are sacrificing quite a bit, like 1 mark out of 3 to get a hint, but it means that you can actually progress. If you have no idea what to do, at least you can kind of piece some things together. Okay. Okay, let's try 9c here. So here we have tan squared x minus cosine squared x. So that is our left-hand side. And, oh, I guess going back to the previous problem really quickly here, I conclude, therefore, left-hand side equals right-hand side. And so therefore, cos squared theta minus sine squared theta over cos squared theta plus sine theta cos theta equals 1 minus tan theta. Just some housekeeping, right? Final statement, always good to have. Okay, so on 9c here, our left-hand side is tan squared x minus cos squared x, and our right-hand side is 1 over cos squared x minus 1 minus cos squared x. Huh. This kind of looks a bit tricky. Anyone have any suggestions on where they would want to start?
Could you turn the right side into like would you want to flip it into something else, I guess? Like the 1 over cos?
Yeah, so actually I think that's a good place to start, right? Like I look at the left-hand side and I don't really have any sort of, like there's no fractions there to begin with, right? So that kind of suggests to me that my first order of business is probably to deal with this 1 over cosine squared and try to get rid of my fractions, or at least try to simplify this as much as I can, right? So the first thing that I'm going to do on the right-hand side is I'm actually going to find a common denominator. Okay, so let's give this a try here. So with my common denominator, oh, here, there we go. I want to put everything over a cosine squared. Okay, so the first term won't change, right? That'll stay the same. Minus, now 1, I'm going to multiply that by cos squared over cos squared. So I'll have cos squared x over cos squared x. And then the minus cos squared x, I'm going to write that as cos to the 4x. So cos to the power of 4x over cos squared x, right? I want to make sure that that 4, we know it's in the exponent, right? Actually, that is one point that I want to make here. Be careful with what is an exponent and what's like a double angle formula, just because I see people mix that up pretty frequently. Make sure that your exponents are like clearly an exponent and not like, so make sure you're not confusing these 2 things. Cosine 2x and cos squared of x, they look kind of similar, so just keep that straight. Now I found a common denominator, which is great. Let's kind of combine these. So I have 1 minus cos squared x minus cos 4x over cos squared x. So it kind of looks like I've made this more complicated, but it actually ends up being a little bit simpler, okay? Now looking at this, does anyone have any ideas of where they might want to go next?
Could you make it so it's like something being multiplied so you could like cancel?
Okay, yeah.
The cos squared x.
Okay, so you guys are saying like, okay, let's try to cancel some things out to make it look a little bit more simple, right? But looking at this expression, uh, because not everything has a co-squared, I can't do any cancellation, which kind of sucks, right? So I can't do any cancellation, which is very frustrating. Which means that, I don't know, I'm kind of stuck, right? Well, I'm not actually stuck, but I'm imagining you guys and we're kind of stuck here. We can't really progress it. So whenever I get stuck, let's go to the other side and fiddle with that for a little while to see if we can make some progress there. Okay, so let's flip over to the left-hand side. Let's give that a try, okay? So looking at that, okay, I have a tan squared, right? Notice that on the right-hand side, I don't have any tans at all. So my first order of business, let's get rid of the tan and let's put it as a sine over a cosine, because at least that's helping me progress a little bit, right? So instead of tan squared, let's write sine squared x over cosine squared x minus cosine squared x. Okay. Okay, so now we're kind of seemingly making some progress. At the very least, we have the same denominator. So things are kind of getting there a little bit, slowly but surely.
Oh,
Now,
you could do like cos squared x and then like multiply the top half, because then you get the cos like to the power of 4x.
very good. Exactly. Yeah. Very good. And that's actually one of my main recommendations here, right? You always want to kind of compare both sides of the equation or the identity that you're trying to prove and use both sides to help guide your answer, right? So Natalie, you notice on the right side, we have a cos of the 4. On the left side, you recognize that if we find a common denominator, that will turn into a cos of the 4, and we're getting that much closer towards proving this thing, right? Very good. So let's find a common denominator here. So in this case, we have sine squared x over cos squared x minus, now this would be cos to the 4x over cos squared x. Okay, so that's looking pretty good. And now we can combine. So sine squared x minus cos 4x over cos squared x. Now it really seems like we're getting somewhere, right? It really seems like we're making some good progress. Just comparing these two sides, already we see some strong similarities, right? We have a minus cos to the 4 over cos squared in both pieces, okay? However, we have a little bit of a problem. We have a sine squared on the left side, and we have a 1 minus cosine squared on the right side.
Doesn't sine squared x just like convert into 1 minus cos squared x? Like, isn't that just a property?
It is an identity, right? So whenever you see something like that, where you recognize that most of the structure of each side looks the same, that's when it's probably wise to head over to your formula sheet to see that if there's any identity that would relate those two together. And Natalie, you're exactly right. So if I look here under Pythagorean identities and quotient identities, these are actually ones that you would have seen in hopefully in grade 11 when you did trig there. I noticed that I have this sine squared plus cos squared is equal to 1. So I know that I have sine squared x plus cos squared x equals 1. And I'm totally fine to just rearrange this thing. So I can flip the cos squared over to the right-hand side. So this would be sine squared x equals 1 minus cos squared x. And then that piece I can use to simplify, either of these expressions, right? Once I make that connection, then I'm good to go. I'm done. So this side, I just replace sine squared with 1 minus cos squared x minus cos 4x over cos squared x, and I'm done. That's it, that's all. All right. So hopefully you're seeing that like it's not always applying trig identities. Like usually I'm only flipping over to this page like near the end once I'm nearly finished, just to kind of wrap things up. Okay.
So like first always simplify, and then once you've gone as far as you can go, then like you should be able to solve it.
Exactly. Yeah, exactly that. Actually, is there? Yeah, let's do one. I know I'm still keeping you guys. Let's do one more that deals with the double angle stuff, because those ones are actually a little bit more, perhaps a little bit more tricky. So Let's try here. Maybe one of these guys, one of number 11. See that this is like a thinking problem, so these are generally harder. So don't judge me if I don't get it first try, although I'm pretty good at this, but again, I'm not perfect by any means. So let's try one of these guys. I don't know, maybe 11A, presuming that one's a little bit simpler than the other one, so hopefully I get this one right. So here we have cosine of 2x plus 1 over sine 2x. So immediately we have some double angle identities going on, so we'll have to use the double angle formulas here. So there's our left-hand side, and our right-hand side is just cotan of x. All right, what side do we want to start with?
Left side.
Left side, yep. Left side is more complicated side. I would say let's start there. And with the left side, what I'm going to do is I'm going to convert all of these double angle formulas, right? I don't really want to deal with the double angle, so I'm going to get rid of those. I'm going to convert those away. So in this case, I'm actually not doing any simplification first. I'm actually going through and doing, I'm replacing all of these with different expressions. So I'm actually going to the trig identities first. Whereas in the last question, trig identities was kind of the last thing I did. So this example in particular shows that really there's not one right strategy to approach here. Every question kind of works in a different way, okay? But you should have both things that you're trying to do in your mind, right? You want to not only simplify or factor or something like that, but you also want to do trig identities. So it's kind of a balancing act. So in this case, I know that cos 2 theta, now I have three choices here. I have 2 cos squared minus 1, cos squared minus sine squared, or 1 minus sine squared. Now, one thing I recognize is that if I use the first one here, cosine 2 theta equals 2 cos squared theta minus 1, because I have a plus 1 in the numerator, I'm going to get some nice like cancellation of the ones, which is kind of preferable, right? It'll make this a little bit simpler. So I'm going to apply cosine 2 theta equals 2 cos squared theta minus 1. And I mean, sine 2 theta, I only have one formula for that, so let's apply that. Sine 2 theta equals 2 sine theta cos theta.
Wait, so is that on the right side?
This is for the left side.
Oh, okay.
Right? So all I'm doing is I'm replacing cosine 2x and sine 2x with those expressions. So let's see what that will get us when we do that. So cosine 2x, that's 2 cos squared x minus 1 plus
Wait,
1.
Replacing the 2x in the cos 2x?
You're not replacing the 2x, you're replacing cosine 2x with 2 cos x minus 1. Because that's what the double angle identity tells you to do. Does that kind of make sense, Aiden?
The one that's highlighted?
Yep.
On the
Yeah.
right, on the textbook, I mean.
Oh, sorry, you're using this formula, right? Cosine 2 theta equals 2 cos squared theta minus 1, and you're replacing that in the left side.
Okay.
Yeah. And similarly, I'm going to do the exact same thing, but with sine 2x, right? I'm going to replace it with sine 2 theta there. Same idea though. Okay, so when I do that replacement, I get 2 sine theta, or 2 sine x cosine of x. And I'm replacing that there. Okay. Now, it may seem like I've not done much, but this is actually going to simplify really nicely from here out. Okay, so right now these brackets in my numerator, these brackets here, they're not doing much. So I'm actually just going to get rid of them. So here I will have 2 cos squared x minus 1 plus 1 over 2 sine x cosine of x. I have minus 1 and I have a plus 1, so those will just cancel out with each other, right? Minus 1 plus 1 gives me 0. So this is 2 cos squared x over 2 sine x cos x. And now what happens now? What happens here?
Can you cancel out one of the cos x?
You can cancel out certainly one of the cosine x's. What else would you be able to cancel, Aiden?
2.
2. Perfect. Yep. So we can cancel out a 2 from top and bottom. And we can get rid of one of the cosines in the numerator, and that'll just kill off the one in the denominator, right? So here we have cosine of x over sine of x. Once all is said and done, all the cancellation has taken place. And cos x over sine x, that's equal to cotan x, which is exactly what our right-hand side is equal to. So at this stage, we are finished. Man, trig identities are so fun though. Like, they're actually very fun, especially when you get a hard one and you don't know where to go with it. Oh, damn, they're good. They're very good. So definitely a bit of a different class today, but I don't know. What do you guys think? Pretty helpful?
It was really helpful, yeah.
Nice. Okay. Cool. Yeah, so test is either going to be Monday or Tuesday. We'll kind of see how tomorrow goes, because tomorrow is a pretty big lesson, pretty important lesson. The idea tomorrow is we're going to be solving things like, just to give you guys a little bit of a preview, we're going to be solving things like 2 sine x is equal to 1. And our job is going to be figure out what x is. Okay, so this one's going to be a little bit more challenging. But I mean, we'll chat about how to find these things. Again, I would say tomorrow's lesson is probably my favorite thing to do in trig. Well, other than trig identities, but those are a little bit different. Solving trig equations is quite fun, quite enjoyable. All right. So our goal tomorrow will be to figure out what x is in these types of equations. Yeah, and then test Monday or Tuesday. I'm leaning towards Tuesday. Just Monday we can take as a review day or introduce the next topic. And yeah, we're nearly on our last 2 chapters. So things are coming down to the wire. One last thing before we head off. Has anyone started the final problem set, or the first part of the final problem set here?
Not yet.
Okay. Make sure. Here, let me just flip to it. Make sure you guys start it, because a lot of it is stuff that you can already do. Like this first part here is just transformations. So state what types of transformations are. Given a point on the original graph, find it after the transformations have been applied. We have a piecewise function. So what value of k will make this continuous? Or can you find a value of k that will make this continuous? State the degree, leading coefficient, and behaviors, so on and so forth. So state properties and then factor. Number 4 is kind of a word, like a rate of change word problem. Number 5 is a box question. Of course, it's a box question. But this one's an inequality, right? Because we're trying to find a volume greater than 4,000 centimeters cubed. Solve some polynomial equations. A rational equation word problem. So Nick and Adam are organizing a car wash. They each take a different amount of time, but when they work together, they can wash a car in a certain number of minutes. And number 8 is just a rational inequality. So these are all types of problems that we've already been doing. You've already seen a lot of these questions on tests. This is due just under 2 weeks from now. So it's due at midnight on June 15th. So make sure you're trying, say, like a couple of these every day. Just get them out of the way. You can do all of these now. Just try to get them finished if you can. Okay. I'll be posting the second set of problems. So this is the first 8. I'll be posting the second 8, hopefully today or tomorrow. So there are quite a few problems. Just make sure you're making some headway every single day. All right. And I'm down to help you guys with this. So if you guys need any help with any of these, let me know, and I'll give you some hints. Okay.
Okay.
Cool. Alrighty, guys. I think that's it. So I guess I'll see you. Yeah, I guess I'll see you all tomorrow.
Yep.
Thank you.
All right. Bye, guys.
See you later.